Hello there students! In the last video I mentioned that there is an extremely great limit of distance in the source engine. This value is something I found only recently. But how is it possible to visit this boundary? After all, 340 undecillion is really high, and no-clip speed is capped by default at 1500 hammer units per second. Before finding out how to visit it, we need to talk about the limit itself. How can it even be that high? Well, that's due to the way the values are stored in the source engine. Positions are stored in a 3D position vector, which is a set of 3 values stored together. Other examples of vectors in Team Fortress 2 include rotation and item colours. These 3 values as individuals are called floats. The source engine uses 3 float values as vectors. In layman's terms, a float is a posh word for a decimal value. Floats, much like all data types in programming, have limits. There's going to be a minimum and a maximum. The maximum of a float value in the source engine's language, C++, is typically 32 bits, and in a numerical value, that limit is... I've got to say this time, haven't I? Right. 340 undecillion, 282 decillion, 346 nonillion, 638 octillion, 528 septillion, 859 sextillion, 811 quintillion, 704 quadrillion, 183 trillion, 484 billion, 516,925,440. Now, I want to go off on a tangent here to show you all something interesting. What happens when you start to go too far? Upon reaching a certain point, you'll notice that the first person model slowly starts to corrupt in an unsettling fashion. This effect is just going to keep getting worse the further out we go. But what exactly is this? Well, you see, it has something to do with a process called floating point precision. Rendering in a 3D space is done through a series of polygons, which are placed in the world relative to the origin, which is the 000 point, using extremely precise decimal values. Well, this is where the problem arises. Because of how float values have limits, not every single decimal number can be a float. And as these floats get higher, these values get more problematic, and you'll find out why soon. I need to explain how float values are processed, and I'm going to avoid getting too technical and explain slowly. As you probably already know, a bit is a single binary value, alternating between 1 and 0. All data types in programming can be represented through bits. For example, you can use a single bit to represent true and false, whilst 8 bits put together can represent 0 to 255. In future, we're going to call this sequence of 8 an 8-bit integer. Starting from the right side of an 8-bit sequence, the binary value 1 will represent the number 1. As we move on to the left, every number from that is multiplied by 2. So the next few will be 2, 4, 8, 16, 32, 64, and 128. You can get the integer number from this by adding all of the 1 numbers together. For example, 010001000 would mean that the values 64 and 4 are both 1. So you can add these 2 values together to make 68. Quick bit of trivia as well, the infamous level glitch of Pac-Man actually happens because it cannot show a 256th root. It overflows the bounds of an 8-bit number, which actually affects other parts of the game. Whilst an integer is 8 bits, a float value is 32 bits, and the 32 bits of a float value consist of 3 separate parts. Again, it's best to start from right to left. Starting from the right, 23 of the bits are the significand value. Although it's hard to explain how, since not even I understand it, just know that these values can form a lot of decimal values from 1 to 2. 2 can't be made though, so the highest possible value from the significand section is 1.9999999, 7 nines. The next 8 values are 8-bit integers, ranging from -127 to 128. I know I said earlier they're usually 0 to 255, but this is a different kind called a signed integer, which has the same number range of 255, but starts at -127. But it's the same aside from that. This integer is the exponent, or the power. The significand value is multiplied by 2 to the power of the exponent value. The exponent value of -127, being all zeros, is used for numbers that fall below the range of a typical floating point number. 128, being all 1, is reserved for special numbers. The last value is the sign, which stores if the value is positive, which is 0, or negative, which is 1. Through exponents and significans, it's possible to represent a lot of numbers with a lot of decimal places. There are certain values that can't be represented. For example, one such number is 6908.4396. This value is not covered by floating points. No matter how hard you try, you cannot convert it into a proper binary float value. But there is a workaround for this. All you need to do is round it to the nearest possible value that can be represented by a float. The closest value to 6908.4396 is 6908.4394533125. This isn't a problem, we're just off by our original number by 0.000146875, which is too small to notice the difference. But the higher we go, the more inaccurate the rounding process becomes. For example, the number 1 trillion cannot be represented as a float. Instead, it must be represented by 999,999,995,904, which is the closest possible value. This is 4,096 off from what we wanted. Are you starting to see the issue here? When the game needs to increase the precise value, it will also need to sacrifice the accuracy. Under regular circumstances, this isn't a problem, since maps can only be within the range of 32,766 hammer units. But going further means that we need to sacrifice decimal accuracy for higher integer numbers. This is a common problem in pretty much every 3D engine, and there's no proper way to fix it. This is what happens to the polygons in the model. Accuracy is sacrificed for higher numbers, and since polygon meshes need to be extremely accurate in order to render properly, this results in the vertices, basically the corners of each shape, trying to find the closest possible area it can be in. This floating point issue even happens with the position values. Floating point precision errors can happen to anything represented by a float data value, and if you get up to a really high distance, it can have adverse effects on the player's positioning coordinates. So, how do you get up to the maximum value? Short answer? You can't under regular circumstances. Long answer, you can, but you need server plugins. When changing the speed of node clipping to get there manually, it would take hours, probably even days to get there. The only way is to teleport using server-side plugins. So I threw together a hastily made plugin and visited the location. What was there is exactly what you'd expect. Nothing. It's basically the same as everything else, and if you try to teleport beyond that, it won't let you. This is probably a disappointment to you, but I'm hoping that you took something from this. After all, this is one of my more technical videos, and from this point on, the subjects of my videos are only going to get more technical and more complicated. So get ready, goodbye for now, and class dismissed. Hello there, students! God damn it, that's a bit too enthusiastic, isn't it? What the hell? 340 undecillion, 282 decillion, 346 nonillion, 638 octillion, 530... Fuck me. Hello there, students, I'm your host, Professor Heavy. Let's get right into the news! 340 undecillion, 282 decillion... How do you get up to the maximum value? Short answer, you can't, you dumbass. 340 undecillion, 282 decillion, 346 nonillion. It's nonillion! When changing the speed of node clicking. Node clicking. 925,440! Oh my god. Oh my god, I went through way too many takes for that.